Hello guys, welcome to my channel, and in this video I'll explain you article number 2.11 Capacitors and Capacitance. Okay, so let's start. A capacitor is a system of two conductors separated by an insulator. Okay, you can see in the figure there are two conductors here and they are separated by a medium, that is a dielectric. Here it is air, it can be any other medium also. Okay, so two conductors separated by a dielectric or a medium is a capacitor. This arrangement is a capacitor, and this has a positive charge. Okay, and these have equal and opposite charges, positive and negative. Okay, so this is a capacitor. Now the conductor have charges, say q1 and q2, and potential v1 and v2. Okay, so this two you can see in the figure. This has charge plus q and this is minus q charge, the second conductor, and they have different potential v1 and v2. Now next, usually in practice the two conductor have charges q and minus q with potential difference v is equal to v1 minus v2 between them. We shall consider only this kind of charge configurations of the capacitor. Okay, so as you can see, the charges have equal and opposite. Okay, and the potential difference will be what? Some difference of this to v1 minus v2 will be the potential difference between two charges conductors. Even a single conductor can be considered as a capacitor by assuming that the other at infinity. Okay, so even if we take a single conductor, we can consider this as a capacitor if the other conductor can be considered at infinity. Okay, so now, but we will understand in this way where two conductors are separated by a dielectric. Okay, now the conductor may be so charged by connecting them to the two terminals of battery. Q is called the charge of the capacitor. Through this, in fact, is the charge of the conductor. The total charge of the capacitor is 0. Okay, so how did we charge these two conductors? So we must have connected them to a battery, and when we connected them to a battery, then positive charges will flow, sorry, this way. We'll connect this way. Okay, the positive side will be like this. Okay, so the positive charge will flow on this and the negative charge will flow on this. So the battery, in pushing these charges into conductor, has done some work. Okay, suppose when the battery pushed one charge, okay, so there was no work done because there was no other charge. But when the battery pushed the second charge, okay, it had to do a work because the first charge had was experiencing, or the first charge was applying a force or repulsion on the upcoming charge. Similarly, as the battery is pushing more and more charge, it has to do certain amount of work. Okay, similarly here the negative charge has been stored. Okay, so you see, in doing this, in charging this two capacitors, the battery has done certain work, and that work has been stored in the form of energy. So this imbalance of charges has, there is a energy stored in electric energy stored. Okay, and there will be, you can see there is a electric field in between. So we can say that electric energy stored in the form of electric field in this two conductor, that is the whole capacitor. And one more thing is there, the net charge of this whole conductor, whole capacitor is 0. Okay, so now the next thing we'll discuss is the electric field in the region between the conductor is proportional to the charge. Okay, so yeah, the electric field is proportional to the how much charge this will have. If this will have more charges, then the electric field will be more stronger. Okay, and more amount of energy will be stored in this arrangement. Okay, that is, if the charge on the capacitor is say double, the electric field will also be double at every point. Okay, so it simply means that if we double the charges, then the electric field will be double. This followed from the direct proportionality between field and charge implied by Coulomb law and the superposition principle. As you know, electric field is directly proportional to the charge. The more you give the charge, the more will be the electric field intensity, okay, at a distance. Now potential difference V is the work done in per unit positive charge in taking a small test charge from the conductor 2 to 1 against the field. Okay, so what will be the potential? I'm saying that this has a potential difference. Okay, what does that mean? It is the, as you know, the definition of potential, it is the work done in moving a test charge. So this is electric field in this direction. Okay, so if I have to do work I have to move a unit positive charge from this conductor to this conductor. I have to do certain amount of work, okay, and that amount of work per unit charge for this charge will be the potential difference. Okay, so this is the potential difference, simply the work done per unit charge or the energy per unit charge. Okay, so and this energy or this work done has been done by the battery. Okay, so this work has been stored in the form of energy in the electric field, as I already told you. So capacitor has stored certain amount of energy, so we have stored energy in this arrangement. Okay, you can ask that in a battery we also have energy stored. So in that, the energy is been stored in the form of chemical energy. Okay, the chemical energy is converted to uh, electrical energy. And also one more difference in capacitor, this is the advantage, capacitor has an advantage, like we can take the energy of a capacitor at all at once. Okay, the capacitor can be discharged in a very few milliseconds. Okay, but in a battery it will discharge at a slow pace. So whenever we need energy at a very fast pace, like you see in a camera, in a flash of a camera, the whole energy has to be converted in a few um, in a nick of a time, you can say. Okay, so in that we need a capacitor. Similarly, when I don't know the name of the device, but when someone when doctor use it, someone is the patient heart is not beating, then we put a device that has a capacitor that will make his heart run again. Okay, okay, pump again. So that there also we need a capacitor. So you see in capacitor it discharges a lot of energy in a very short period of time, very short period of time. So now this energy has been stored. Okay, and this work done, the potential difference is there. Consequently, V is also proportional to Q, and the ratio Q by V is a constant. Okay, and this V is also proportional to Q. Why? Because as we, if I keep moving this positive charge from this to this, okay, this conductor to this, then the potential difference will keep increasing. Suppose at this instant the potential difference of this has a potential difference of 10 plus 10 is the minus 10, the potential is plus, so the potential difference is 20. Okay, if I take more positive charge from here and take it to the first conductor, then the potential difference will more increase more. Okay, and we have to understand that this ratio of the charge or potential is always a constant. Okay, because B is proportional to Q, this ratio is always a constant. Okay, so this constant is called capacitance. So capacitance is what? It is the ratio of charge upon potential. As we keep increasing the charge, the potential difference between the conductor will keep increasing. Okay, this is our constant capacitance, and C is independent of Q or V. Okay, it is independent of Q or V. It doesn't depend on either charge or capacitance. Okay, capacitance depends only on the geometrical configuration, shape, side configuration of the system of the two conductors. Okay, it depends on the shape, size. Okay, bigger the conductor, the more will be the capacitance. Okay, the size will be more, the more will be the capacitance. It doesn't depend on charge and potential. Okay, now and it also depends on the insulator that is separating the two conductors. We'll see in the next paragraph that when we insert a dielectric in between with a with dielectric constant more than 1, then the capacitance value will increase. We'll see it later. The SI unit of capacitance is 1 farad, or the SI unit is 1 farad, and you can define 1 farad. Okay, so 1 farad is 1 coulomb per 1 volt per volt. Okay, so if suppose if I take 1 coulomb charge from this to this, okay, if I move 1 coulomb charge from this conductor to this conductor, then if the potential difference increases by 1 volt. Okay, if on moving 1 coulomb charge from this conductor to this conductor, there is a potential difference of 1 volt, increase of 1 volt potential difference, then I'll say the capacitance of this is 1 farad. Okay, 1 farad is a very big unit, so we use a smaller unit. Practical units are microfarad or picofarad. Okay, a capacitor with fixed capacitance, symbolically, yes, as this is a symbol of a capacitor, and it has a fixed capacitance. Okay, that is, it cannot be changed. And now in a variable capacitor, the symbol is this. We'll understand how can we change it. Okay, we can change the distance between them, we can increase the area if somehow, then we can change the capacitance. Okay, but we'll move to the next paragraph now. Equation 2.38 shows that for large C, V is small for a given Q. This means capacitor with large capacitance can hold large amount of charge Q at relatively small V. Okay, so I'll make you understand this with example. You know the formula, C is equal to Q by V. Okay, so suppose I have two capacitors. Okay, the for first capacitor the value of capacitance is 1. Okay, and for the second is 2. Okay, so now how can I get 1? If I have suppose 10 charge. Okay, 10 charge. So how can I obtain 1 for the first capacitor? I have to give 10 volt. This ratio has to be constant. Okay, 10 upon 10 should be 1. In the other case, I'll think the capacitance is 2, and I am giving the same charge for this. How can I obtain 10 for this, 2 for this? If the charge is 10, so you will say this has to be what? 5. Only then I will obtain 2 here. Okay, so because this ratio has to be constant. Okay, so now you see in the first capacitor, this is first capacitor, remember this is first capacitor, this is second capacitor. Okay, so in this case you see, for giving 10 charge, for the capacitor to hold 10 charge on each of the conductor, so 10 coulomb you can it can be 10 microcoulomb, whatever, but we are not concerned with the unit, just say 10 charge. Okay, and this is 10 charge. For holding 10 charge, the voltage has to be 10 volt. There will be increase of 10 volt, you can say, and in this case for the same 10 charge, the voltage potential difference of voltage is 5 volt. So you can see a capacitor having a larger capacitance 2, here is 2, we can give same, it can hold more charges in the small potential difference. Okay, in small potential difference it can hold more charges if it has a large capacitance. This is a very important part you have to understand. Okay, now this is a very important implication. This is of practical importance. A strong high potential difference implies strong electric field around the conductor. A strong electric field can ionize the surrounding air and accelerate the charges to produce the oppositely charged plate, thereby neutralizing the charge of the capacitor plate at least partly. In other words, the charge of the capacitor leaks away due to the reduction in insulating power of the intervening medium. Okay, so in charging a capacitor, okay, we have to keep the potential as low as possible. Okay, why so? Because like when I am giving this charge, okay, when I am giving this charge, this positive charge I'm giving it here, I am taking this positive charge from here to here. Okay, as I am increasing the positive charge here and negative charge here, the potential is also increasing. Okay, the potential difference or the potential is also increasing, and when V is increasing, from the relation E is equal to V by D, that what will increase? The electric field will also increase. When our potential is increasing, the electric field will also increase, and when electric field will increase, the value of electric field will increase. What will happen? Then? There dielectric. Suppose this is air has molecules like this. Okay, so this electric field become so strong as I'm increasing the voltage on moving the charges. Okay, then the electric field will ionize the air, like it will attract the negative charge towards it, and it will attract the positive charge towards it, and those charges will neutralize this negative charge will neutralize one positive charge here. Similarly, there are other atoms that will be ionized, so it will neutralize the charges on it. Okay, similarly, so there is a limit, there will be a limit up to which we can charge the capacitor. Okay, so if suppose the value is I've reached 90 electric field, then there is no problem. But as soon as I reach 100 electric field, Newton per coulomb, then what happens? The the medium start ionizing, and the charge start leaking. how the charges are leaking? Because this charge has been neutralized by the charge of the air. Okay, so no more charge can be stored. Okay, so if I want to store more and more charges, I want this conductor to hold more and more charges, I have to give the potential as low as possible. Otherwise the electric will be so strong and it will neutralize the medium or the air, if the medium is air. And what will happen then the charge will start leaking. Okay, so this is called the dielectric strength. Okay, I hope I was able to make this clear. This is very important. So we have to we want to take a capacitance, capacitor having high capacitance has a significance. Then in that we can have more charges, hold more charges in a small value of capacitance, as I told you from the example. So now the maximum electric field that a dielectric medium can withstand without breakdown of its insulating property is called dielectric strength. So what is dielectric strength? The maximum electric field that a dielectric medium can withstand. Otherwise it will be ionized. Okay, and the conductor will be neutralized. They will not hold more charges. The charges will be start leaking, we can say. Okay, for air it is 3 into 10 to the power 6 volt per meter. Okay, so this is the value of the dielectric strength for air. For a separation between conductors of the order of 1 centimeter or so, this field can correspond to a potential difference of 10 to the 3 into 10 to the power 4 volt between the conductor. Okay, for 1 centimeter the electric field has to be 3 into 10 to the power 4 volt. Beyond this the charger will start leaking. Okay, thus for a capacitor to store a large amount of charge without leaking, its capacitance should be high enough so that the potential difference and hence the electric field do not exist the breakdown limit. As I already told you, if I take the capacitance as high as possible, okay, if I make the capacitance as high as if I take a conductor of high capacitance, then it can have more charges in low potential difference. Okay, we don't want the potential difference to increase, otherwise there will be leakage. Put differently, there is a limit to amount of charge that can be stored on a given capacitor without significant leaking. This I also explained you. In practice, the farad is very unit. The common units are 1 microfarad, nanofarad, picofarad. Besides its use in storing charge, a capacitor is a key element of most AC circuit with important function. Okay, when we see AC chapter, then we'll see the importance of capacitor. Okay, so I hope I was able to make you understand this capacitor and capacitance. Okay, this is a very important topic. Okay, in this chapter also, and in other further chapter. Okay, and in the next video we'll discuss about the parallel plate capacitor. Okay, so till then, thank you. And if you like this video, please give it a thumbs up, like this video, then so that it will be recommended to others. When you like this video, it will be recommended to others. Okay, and subscribe to my channel, hit the bell icon also, so that you get the notification on my videos. Okay, so thanks for watching.